Today we'll have William Harding, who will talk about Chern-Simons-Trinion theories, SUSY Enhancement, one-form symmetries, and Hooft Anomalies. Take it away.
Okay, so thank you very much, Julius, for inviting me to give this talk. It's really a pleasure to speak at the Quiver Meeting. So today I will speak about Chern-Simons-Trinion theories. So this talk is based on a work which I did together with Riccardo Comi and Nopalo Vicaviglia, both at University of Milano-Bicocca. And so I will start with an introduction. And so since there is the word trinion in the title, let us say what a trinion is. So the for d(n) equal to 2 Tn theory arises from the compactification of the 6d(n) equal to 2,0 theory of type an-1 on a Riemann sphere with the 3 punctures. And the flavour symmetry algebra is SUN cube. Now for n equal to 2, this is the theory of 8 real fibers in the trifundamento of SU2 cube, whereas for n equal to 3, the flavour symmetry algebra is enhanced to E6, and this corresponds to the rank 1 E6 SCFT. Now, for n bigger or equal than 3, there is no for d(n) equal to 2 Lagrangian description. However, in the case n equals to 3, there are for d(n) equal to 1 Lagrangian description with an SUSY in the infrared. And now the 3d(n) equal to 4 Tn theory is obtained by compactifying the 4d(n) equal to 2 Tn theory on a circle, or equivalently by compactifying NM5 planes on a circle times a sphere with the 3 punctures. And since in this talk I will deal only with the 3D theories, from now on I will denote with the 3d(n) equal to 4 Tn theory simply as the Tn theory. Okay. Now, the flavour symmetries of the Tn theory can be gauged in interesting ways. For instance, we can take one or more copies of Tn and gauge each common SUN global symmetry factor with 3d(n) equal to 3 Chern-Simons levels Ki, with I going from 1 to 3. So here I drew 2 cases, the case in which we have one Tn, whose flavour symmetry is gauged with Chern-Simons levels K1, K2, and K3, and also the case with 2 Tn, and I gauge each common SUN factor with Chern-Simons levels K1, K2, and K3. Now, the manifest amount of SUSY of such theories is 3d(n) equal to 3. However, it was proposed by Asserta, Chikawa, and Tomasiello that if the following condition holds, namely the sum of the inverses of the 3 Chern-Simons levels is equal to 0, then the corresponding infrared SCFT has n equal to 4 SUSY. Now, we call this the ATT condition, and this is a sufficient but not necessary condition for SUSY enhancement. Indeed, I will show that even if the ATT condition is not satisfied, there can be infrared SCFTs with n equal to 4 SUSY. Okay, so before giving a description of the field theoretic proof of this SUSY enhancement, let us look to the geometric picture. Now, there is a vast literature on 3D theories that arise from compactifying 6d(n) equal to 2,0 theories on 3 manifolds. And so we are interested in type an-1. This can be compactified on S1 times S2, where S2 has 3 punctures, whose boundaries are denoted by Bi with I equal to 1, 2, or 3. Moreover, let us denote with Fi the associated S1 fiber for which Bi is the base surface. Now, we fill each boundary by attaching it to a solid torus, S1 times D2, with S1 equal to Bi prime, and the boundary of D2 equal to Fi prime. Such that in this screwing, we perform an SL2Z action, which is governed by this element of SL2Z, which I denoted as Gi, which is taken to be T to the Ki. Now, the action of T to the Ki gives rise to the Chern-Simons levels K1, K2, and K3. The corresponding geometry is a ciphered manifold of genus 0 and ciphered parameters 1 over K1, 1 over K2, and 1 over K3. The corresponding field theory picture is this one. So one copy of Tn whose flavour symmetry is gauged with Chern-Simons levels K1, K2, and K3, corresponding to the Seifert parameters. Now, in this case, if the ATT condition is satisfied, n=4 SUSY enhancement can be proved via geometry, as stated by Asselta, Chikawa, and Tomasiello. Okay, now we can do basically the same kind of thing from the geometric picture if we want to build theories with multiple Tn building blocks. So let us focus on 2 copies of Tn. Now we can group together 2 copies of S1 times S2, where S2 has 3 punctures. For each puncture, there are these boundaries, B, with a capital I index, and the capital I index can be equal to 1 or 2 because it is associated to each of the 2 copies. We also denote by F with capital I the associated fibers for which the BIs are the base surfaces. And now we can group the B's and the F's of the first copy with the B's and the F's of the second copy together. And we identify them by this GI, which is an element of SL2Z, taken as before to be T to the KI. And now the corresponding geometry is a graph manifold, because basically it corresponds to, in this case, 2 Seifert manifold building blocks. Now the corresponding field theory description is that of 2 copies of Tn, whose flavour symmetry are gauged with Chern-Simons levels K1, K2, and K3. Now, in this case, if the ATT condition is satisfied, the geometry of the graph manifold does not provide an explanation for n=4 SUSY enhancement. Nonetheless, field theory does, and I will explain this to you in one of the next slides. Okay, so now let us look at field theory and let us consider 1 copy of Tn whose flavour symmetry is gauged with Chern-Simons levels K1, K2, and K3. Now, let us show theoretically why there is n=4 SUSY enhancement, if the ATT condition is satisfied. Now, given this theory, let us denote with phi I the adjoint scalars in the ith n=3 Chern-Simons vector multiplet, and with mu I the moment map operators for the SUNI symmetry of Tn. Now, the superpotential in 3D n=2 language, where SO2R is manifest, is the one which I wrote down. And note that there is this first term which contains Chern-Simons levels Ki, which we assume to be non-zero because we want them to be non-trivial, the Chern-Simons levels. Now, the second term contains these moment maps mu I. And to be more explicit, let us consider a specific example, which is T2. So in this case, the moment maps are particularly simple because if we denote with Q, I, J, K, the trifundamentals of SU2Q of the T2 theory, then the moment map operators are simply these 3 guys, which I wrote down. And they also satisfy the following relation, which in the case of T2 is actually quite simple to prove. The important fact is that this relation satisfied by the moment map operators can be generalized to the general n case, so to Tn. And in this case, we have that trace of mu1 to the k is equal to trace of mu2 to the k, which is equal to trace of mu3 to the k, where k goes from 2 to n. And since these 3 objects are equal, we will denote them simply as trace of mu to the k. And starting from this condition, n=4 SUSY enhancement can be derived along the line of the following papers, which I wrote down. Okay, so let us see this explicitly. So, as you know, in 3D n=2 formalism, generically, a 3D n=4 theory has an SO2A or U1A global symmetry, under which the moment map operator mu has charge, say, +2. So, for example, you can consider 3D n=4 UNC gauge theory with NF flavors. Now, in n=2 language, we have the superpotential trace of Q tilde phi Q, where phi is the adjoint scalar, and the Q tilde and Q are the chiral multiples contributing to this theory. Now, the A charge of Q and Q tilde is taken to be 1, and the A charge of phi is taken to be -2. Hence, the moment map operator mu, which is defined as Q tilde, has a charge 2. Now, in our case, so one copy of Tn with the flavour symmetry gauged as SUN level K1 times SUN level K2 times SUN level K3. I report again the superpotential, which is the following one. And as you can see from the following superpotential, SO2A is broken. It does not commute with SO3R. And this is due to the fact that in the superpotential, we have a term which is proportional to the Chern-Simons levels. Okay, now we can proceed as follows. We can integrate out the adjoint scalar fields phi I, and we obtain the following effective superpotential. So basically, this is sum for I going from 1 to 3 of 1 over Ki times trace of mu I squared. Now we can use the condition which I wrote down in the previous slide, satisfied by the moment map operators. So let us recall it. So this condition satisfied by the moment map operators. Let us use this. And we can rewrite the effective superpotential in this simple way. So 1 over K1 plus 1 over K2 plus 1 over K3 times trace of mu squared. Now, this term in brackets, if we take it to be equal to 0, this means that the ATT condition is satisfied. So if the ATT condition is satisfied, the effective superpotential is equal to 0, and SO2A is restored. So concluding, our theory has SO3R that doesn't commute with SO2A in the formalism with manifest SO2R. Hence, it must have SO2 plus 2R, which is SO4R, and SUSY is enhanced to n equal to 4. And this basically is the argument given by Asserta, Chikawa, and Tomasiello. Okay, now before moving on, I will give a brief description of the main results which I will present. So in this talk, I will focus on 1 or 2 copies of T2 theory, gauged with Chern-Simons levels K1, K2, and K3. Now, I will show that even if the ATT condition is violated, there can be infrared SCFTs with n equal to 4 SUSY. Then there are also n equal to 5 and n equal to 6 infrared SCFTs that are variants of the orthosymplectic ABJ theory, and I denoted the Quiver diagram here. So we have an O2M level 2K gauge group and an USP2N level -K gauge group, and they are connected by 2 bifundamental half-hypers. Okay. Next, I will also analyze the one-form symmetries and their Hooft anomalies for this class of theories. And we will see that they constrain the infrared behavior of these theories. And generically, the infrared theory consists of an interacting SCFT plus a decoupled TQFT. The moduli space will be also analyzed by taking the Higgs and Coulomb branch limits of the superconformal index. Then I will also perform a brief analysis of the T3 case, and for the analysis of further generalizations, including more copies of T2 or T2 theories glued with the TSU2 theories, for instance, you can see more details in our paper, or we can discuss at the end of this talk. Okay, so before going on, are there any questions about this introductory part? Okay, so if not, I can proceed. So now, in the next section, I will discuss Chern-Simons theories with a single copy of T2, flavour symmetry algebra gauged, which has Simons levels K1, K2, and K3, and importantly, I will consider theories satisfying the ATT condition. I will study the superconformal index, show that the superconformal index agrees with the fact that there is n equal to 4 SUSY, and I will also study the one-form symmetries and the Hooft anomalies of this class of theories. Okay, so the superconformal index. So this is the supersymmetric partition function on S2 times S1. for one copy of T2, gauged with Chern-Simons levels K1, K2, and K3. It is given by the following expression. So basically, we have an integral over the gauge fugacities, a sum over the gauge fluxes, which I denoted as M1, M2, and M3. Then we will have the contribution of the 3 SU2 vector multiplets, and then we will have also the contribution of the 8-3 R-fibers of the T2 theory. Now, you can see that there is this fugacity A appearing in the index, and this is the fugacity associated to the U1A symmetry. And clearly, if the ATT condition is not satisfied, we have to set A to 1, because this is no more a symmetry of the theory. Okay. So, the general solution of the ATT condition is given by the following expression. So the Chern-Simons levels will depend on 4 integers, 4 non-zero integers. So an overall integer k, and then these integers p, q, and r, where r is defined to be equal to p plus q. And for example, if we take p equal to 1, q equal to 1, and r equal to 2, then the Chern-Simons levels are simply minus k to k and to k. And this theory is equivalent to the spin 4 level 2k times USP2 level minus k gauge theory with a bifundamental R-fiber multiplet. Now, importantly, if the Chern-Simons level satisfies the ATT condition, then the index receives non-zero contribution only from 0 gauge fluxes and from gauge fluxes of this kind. And now in the next slides, I will analyze these 2 kinds of contributions to the index. So let us start with the zero flux sector. So to study SUSY enhancement due to the ATT condition via the index, actually, it is sufficient to consider only the zero flux sector. And the corresponding contribution to the index is the following. Now, for an n equal to 3 index, the coefficient at order x corresponds to the n equal to 3 flavour current multiplet. And since in this case, the coefficient at order x is 0, this means that there is no n equal to 3 flavour current multiplet in our case. Now, you can see that there is also a term at order x squared, which is a to the 4x squared, and this corresponds to the marginal operator trace of mu squared. But we also have a negative term at order x squared. Now, in general, for an n equal to 3 index, the negative terms at order x squared receive the contribution from total conserved currents, including the n equal to 3 flavour current multiplet, but also the n equal to 3 extra SUSY current multiplet. Now, since in this case we have no n equal to 3 flavour current multiplet, the term minus x squared necessarily corresponds to 1 n equal to 3 extra SUSY current multiplets, which is the U1A flavour current. Hence, we have enhanced n equal to 4 SUSY, as predicted by a certa Chikawa-Tomasiello, basically. So, this discussion regards the zero flux sector. Now, we can study also the other non-trivial sector, and we can show that this does not contribute in our argument regarding SUSY enhancement. And this is because of the following fact. So let me explain this to you. So the contributions from these fluxes correspond to gauge invariant rest monopole operators. And how you can see this? Well, you can start from the bare monopole operators associated to such fluxes. You can study their dimension, their charge under U1A, and their charges under the Cartan subalgebra of each SU2 gauge factor of the theory. And so this bare monopole operator, in particular, can be addressed with a particular combination of chiral fields of the T2 theory to form gauge invariant quantities. And then we can study the dimension and the U1A charge of such gauge invariant rest monopole operators. Hence, the contribution to the index is the one I wrote down here. And by studying this contribution, you can actually see that it does not contribute to our argument related to SUSY enhancement. And now I will make a clear example, so this will be much clearer to you. Okay, so the example which I will consider is the one I mentioned also before. So let us take Chern-Simons levels to be equal to minus k to k to k. So this is equivalent to the spin 4 level to k times the spin 2 level minus k gauge theory with a bifundamental alpha per multiplet, as I already told you. And the indices up to order x cube are the ones which I wrote down in the following table. Now, in this case, the dimension of the gauge invariant rest monopole operators, which contribute to the index, is, so the dimension is 2k minus 4 times n, where n is an integer, and the charge under U1A is 4k minus 8 times n. Now, for k equal to 1 and k equal to 2, the dimensions are negative or 0. Hence, the theory is bad in the sense of Gaiotto-Witten, and the index diverges. So we can't do actually anything in this case, because the index is infinity. So let us consider the case k equal to 3. Now, in this case, you can see that there are two marginal operators corresponding to the positive contribution appearing at order x squared. One of them is trace of mu squared, which is due to the zero flux sector, if you recall. But then the other contribution is due to the dress monopole operator contributing a to the 4 x squared for n equal to 1. So you can see clearly that this gauge invariant dress monopole operator does not contribute to our argument related to SUSY enhancement. Here we still have the coefficient at order x equal to 0 and the negative coefficient at order x squared equal to minus 1. Okay. Now, from the indices, we can also actually study the moduli space of this theory. So let us concentrate on general Chern-Simons-Trinion theories satisfying the ATT condition. The moduli space can be analyzed by considering a particular limit of the index, similarly to what has been done by Razamat and Willett. So this limit allows us to extract information on two branches, and I will denote them as Higgs branch and Coulomb branch in analogy with Razamat and Willett. So how can we proceed? So we define two variables, h and c. So h is equal to x to the 1/2 times a, whereas c is equal to x to the 1/2 divided by a. And then we substitute these two variables in the index. Now, in the X branch limit, we send c to 0 and keep h fixed, whereas in the Coulomb branch limit, we send h to 0 and keep c fixed. And doing so, for a single copy of T2 with general Chern-Simons level satisfying the ATT condition, the results are the following. So, the Coulomb branch limit gives us simply 1 as a result, whereas if we take the X branch limit of the index, you obtain the following. And now here you can recognize that the X branch limit of the index can be written as the Petistic exponential corresponding to a D-type Kranian singularity. So the feature of this class of theories is that the Coulomb branch is trivial, and the X branch is isomorphic to C2 mod D capital K plus 2, where capital K, I defined it here, basically is related to the values of the Chern-Simons levels. Now we can study the generators of the X branch, which are the following, which I wrote down here. So we have trace of mu squared, then we have a gauge invariant the rest monopole, then we have also this guy, which I denoted by U, which is basically a pair monopole, the rest with a combination of chiral fields of the T2 theory, and then the rest also with these moment maps, mu1, mu2, and mu3. And now these generators satisfy the defining relation of C2 mod D capital K plus 2, which is the following, which I wrote down here. Okay. So now we have discussed the indices, the moduli space, and as I anticipated to you, I want also to study the one-form symmetries and the Hooft anomalies for this class of theories. And in order to do so...
A question?
Yes, of course.
What is the set of models where you will have enhanced supersymmetry?
Okay, so we have this set of models, which basically are, okay, T2, which are Simons levels satisfying a TT condition. But then I will show you that there is also another set of models, which I haven't discussed yet, where the TT condition basically does not hold anymore, but there is still enhanced SUSY. And I will discuss this in the next section of this talk, basically.
And do you know the moduli spaces in these cases?
Yes, I will basically in the other cases, no, I will explain you why, but the moduli space will be trivial.
Both.
Then yeah, and then I will also tell you about other cases in which well, obviously we can take more copies of T2 and gauge them with Chern-Simons levels satisfying the TT condition. And I will tell you that in such cases, we will also obtain the moduli space, which will be of the type of a D-type Kranian singularity, basically.
Mm-hmm.
Yeah, and I will explain this to you in a few minutes.
So all the models you know have dimension 1 for the moduli space?
For T2, yes, exactly. If the moduli space is non-trivial, we find always something of this kind. Mm-hmm. Yes.
Okay.
Obviously, if instead of T2 you consider Tn, the moduli space will be different. And if I have time, I might say something about the T3 case. I don't know. In case we can discuss after the end of this talk. Yes, but basically for T2 theories, you can take 1 or 2 copies of them, and you will always find something which is a Kranian type, a D-type Kranian singularity, if the ATT condition is satisfied. Yes.
Okay, thank you.
Okay. Thank you. Okay, so now let us go on now I want to study the one-form symmetries of this class of theories. Now, in order to do so, let us start by considering simply the T2 theory with no gauging. Now, the faithful global symmetry group of the T2 theory is SU2 times SU2 times SU2 mod Z2 superscript 1,3 times Z2 superscript 2,3. Well, Z2 superscript I, j is the diagonal Z2 subgroup of the center of SU2I times the center of SU2J. Now, why this relation is true? Okay, I can tell you why briefly. So, because if you write down the character of the trifundamental representation as following, then you can see that there are 2 independent actions of the centers that leave the character invariant, and they are Z2 superscript 1,3, which is the one which sends Z1 to minus Z1, leaves Z2 invariant, and sends Z3 to minus Z3. And then there is also Z2 superscript 2,3, which basically is analogous, is the same. Next, we can gauge the flavour symmetry of the T2 theory as SU2 times SU2 times SU2. And this gives rise to a Z2 times Z2 one-form symmetry. Now we have gauged this flavour symmetry. We want to add n equal to 3 Chern-Simons levels. And turning on Chern-Simons levels, the Hooft anomalies can be characterized by the 4D anomaly theory with, so this is the expression of the 4D anomaly theory. There is this Y4, such that the boundary of Y4 is our spacetime X3. Then there is this W's, which are the 2 form background fields for the ith Z2 conform symmetry. And they satisfy the following condition. So the sum of the 3 of them equals 0. And this is because among the 3 Z2 uniform symmetries that in principle we can have, actually only 2 of them, as we have seen, act non-trivially on the trifundamental matter of T2. And so they satisfy this constraint. Then there is also this P, which I wrote down in this anomaly theory, and P is the Pontryagin square, which is even on a spinfold manifold. Now, from the constraint satisfied by the twofold background fields, the Hooft anomaly can be rewritten in the following way. So you see that there are these coefficients Pij. Now, these Pij are the entries of the anomaly matrix, which I reported here for our case. And this anomaly matrix P is particularly useful to detect which subgroup of the Z2 times Z2 one-form symmetry is anomalous. Indeed, the anomaly free, which means gaugeable part, is Z2 to the dimension of the kernel of P, whereas the anomalous, meaning non-gaugeable part, is Z2 to the rank of P. And now let us see an explicit example of these one-form symmetries and anomalies, which I discussed in this slide. So let us consider our case of Chern-Simons levels minus k to k and to k. So this theory, which I write down here. So the one-form symmetries and their Hooft anomalies are reported in this table. Now, by using the prescription I described in the previous slide, the anomaly matrix for k even is trivial, meaning that the Z2 times Z2 one-form symmetry is non-anomalous. On the other hand, for k odd, the anomaly matrix is non-trivial. And using the prescription I described, you can show that the non-anomalous one-form symmetry is Z2, and the anomalous one-form symmetry is Z2. Now, what does it mean? It means that for k even, the theory flows to an n equal to 4 SCFT with non-anomalous Z2 times Z2 from symmetry, whereas for k odd, the theory flows to an n equal to 4 SCFT with non-anomalous Z2 one-form symmetry, along with the DQFT U1 level 2, which has an anomalous Z2 one-form symmetry characterized by the matrix P, which I wrote down in the table. So also, let me explain this notation which I used for U1 level 2. I also wrote down A, superscript 2, 1, and this is the notation of Sin, Raman, Seiberg. Basically, this means that U1 level 2 is the minimal abelian DQFT with anomalous Z2 one-form symmetry characterized exactly by the anomaly matrix, which I wrote down here in the table. Okay, so now we know which one-form symmetries are anomalous and which are non-anomalous. If they are anomalous, we can gauge them. And in doing so, we obtain the diagram which I sketched here. So we can start from the first line of this diagram, which we already know. So here I reported the gauge groups of the theories. So on the left-hand side, there is the gauge group of the Chern-Simons-Trinion theory, whereas on the right-hand side, there is the gauge group of the orthosymplectic quiver. Now, we can gauge the Z2 one-form symmetry corresponding to a combination of the centers of SU2 level 2K and SU2 level 2K. And I obtain the gauge group, which you can read. And this actually is equivalent to the SO4 level 2K times your SP2 level minus K theory. Now, if K is even, I can gauge a further one-form symmetry, obtaining the gauge groups, which I wrote down at the bottom. Now, let us remark that since in three dimensions, gauging a Z2 one-form symmetry gives rise to a dual Z2 zero-form symmetry, we can go from the bottom to the top by gauging the corresponding Z2 zero-form symmetries. Okay. So are there any questions about this discussion related to Chern-Simons-Trinion theories satisfying the ATT condition? Okay, so if not, I can go on. And now let us consider Chern-Simons theories with a single copy of T2. So this is the picture, But now the ATT condition is not satisfied, meaning that the Chern-Simons-Trinion do not, the sum of the inverses of the three Chern-Simons-Trinion is different from 0 in this case. And what is important about this case is that we find an infinite family of theories which throw to n equal to 4 SCFTs, even if the ATT condition is not satisfied. I will study the one-form symmetries and the Hooft anomalies thereof. And in another interesting fact, which I will explain, is that a family of such theories throw to n equal to 4 infrared SCFTs, which possess also a manifest n equal to 2 Lagrangian description, which was provided by Gang, Kims, and Stubbs later last year. Okay, so let us start. So let us take an example, and let us take the Chern-Simons-Trinion to be equal to K11, meaning that the ATT condition is not satisfied. You can look at the indices. Now, for K equal to 1, the index is equal to 1, and the theory throws to a pure DQFT. This cannot be trivially gapped. We will see that this has an anomalous Z2 times Z2 one-form symmetry, and the corresponding infrared DQFT is identified as Z2 level 0. Now, I will explain this comment in the next few slides. For now, take in mind that the index is equal to 1, for K equal to 1. However, now you can see that for K bigger and equal than 2, the index contains 0x, meaning that there is no n equal to 3 flavour current, and minus x squared, meaning that there is 1 n equal to 3 extra SUSY current. So we have enhanced n equal to 4 SUSY. But in this case, since the ATT condition is not satisfied and we can't turn on the U1 asymmetry, the enhancement is completely accidental. Okay. So let us study more in detail what are these 3D n equal to 4 infrared SCFTs predicted by index computation. So let us still consider Chern-Simons-Trinion K11. For K equal to 2, the index turns out to be equal to the one of the minimal rank 0 n equal to 4 SCFT, where the name minimal comes from the fact that it saturates the lower bound on the S3 free energy. Now, rank 0 means that the Higgs branch and Coulomb branch are both trivial. And so indeed, this is one of the first answers to the previous questions. If the ATT conditions is not satisfied, we can still have theories which throw to n equal to 4 SCFTs. However, the moduli space is trivial in this case, if the ATT condition is not satisfied. Okay. Then let me also explain what, so this minimal rank 0 n equal to 4 SCFT has also another description with manifest n equal to 2 SUSY. Indeed, this is the infrared fixed point of the 3D n equal to 2 U1 level 3 half gauge theory with one chiral multiplet of charge 1 and R charge 1/3. And so, if we take one copy of T2, which are Simons-Trinion 2, 1, 1, this throws at the infrared to the minimal theory times a TQFT, which is denoted as Z2 level 2, and I will explain what does it mean in the next slide. Now, for generic K bigger or equal than 2, we will see that the theory throws to a 3D n equal to 4 rank 0 SCFT, and in all of such cases, there is a manifest n equal to 2 Lagrangian description. Plus, there is also a decoupled DQFT, which I'm going to explain now. So, I already introduced this Zn level K without explaining it. So this is a U1 times U1 Chern-Simons theory with the following action, which I wrote down here. Now, for one copy of T2 with Chern-Simons-Trinion K11, we can study the one-form symmetries and their Hooft anomalies using the prescription I described before. And the results are here in the table. Now, recall that for K equal to 1, the index was equal to 1, meaning that the theory refers to a TQFT, and by looking to the anomaly matrix, you should look to K odd, This has an anomalous Z2 times Z2 one-form symmetry, and the TQFT corresponding to such anomaly matrix is Z2 level 0. Now, for k odd but bigger than 1, we have that the theory flows to an n equal to 4 SCFT with trivial non-anomalous one-form symmetries, along with the TQFT Z2 level 0. On the other hand, for k even, you see that the anomalous one-form symmetry is still Z2 times Z2, but since the anomaly matrix is different, in this case, the TQFT is Z2 level 2. Okay. So now, I anticipated that these 3D n equal to 4 infrared SCFTs that we are able to reach in the infrared also possess a Lagrangian description with manifest n equal to 2 supersymmetry. And actually, this description came out in a paper by Gang, Kim, and Stubbs, which appeared after our paper. And so now I will describe it. So let us consider a 3D n equal to 2 Chern-Simons matter theory with X U1 gauge groups, mixed Chern-Simons couplings, Kij, among them, where Kij are the entries of this K matrix, which I wrote down here. Then we also have chiral multiplets carrying charge +1 and their each gauge group. And then we also have a monopole superpotential when we have gauge invariant Baire monopoles labeled by these fluxes which I wrote down. Now, as shown by Gang, Kim, and Stubbs, this theory flows to a 3D n equal to 4 rank 0 SCFT, which I denote as T of X. And the index reveals that the infrared SCFT of our Chern-Simons T2 theory with Chern-Simons levels K11 is indeed T of X with X equal to K minus 1. However, the decoupled TQFT has to be determined by anomaly analysis separately, as I explained to you in the previous slide. And finally, also note that for X equal to 1, meaning K equal to 2, T1 corresponds to the minimal rank 0 n equal to 4 SCFT. Okay, so finally, I will conclude this section by pointing out a subtle point. So, if we compute the index of two theories, we might find that the indices are the same, and we might conclude that the two theories are dual to each other. But actually, this is not always the case, because it might be that the decoupled TQFT, which can be derived by anomaly analysis, are different. So what does it mean? Now, I will explain this to you in this slide. Let us consider one copy of T2 with Chern-Simons levels K1, K2, and 1. So these theories arise from the compactification of the 6T n equal to 2,0 A1 theory on a length space of R of PQ, where P and Q are related to the Chern-Simons levels as I wrote down. And also recall that R of PQ can be viewed as the quotient space S3 mod ZP, and that R of PQ and R of P prime Q prime are diffeomorphic if and only if P prime is equal to P and Q prime is equal to plus or minus Q to the plus or minus 1 mod P. Now, if we have diffeomorphic free manifolds, this means that the corresponding Chern-Simons T2 theories flow to the same infrared SCFT, because the indices are the same. However, as anticipated, the decoupled TQFTs might differ. So let us consider an explicit example. Let us take one copy of T2 with the following values of the Chern-Simons levels. K11 minus K minus 1, 1, 1, and K minus 1, minus 3, 1. All of these correspond to the length space R of PQ with P equal to 2K plus 1 and Q equal to plus or minus 2. Indeed, they have the same indices. This is not a surprise from the geometric point of view, meaning that they flow to the same infrared SCFT. However, the decoupled TQFT is in general different. For instance, if you take K to be even, the TQFT for Chern-Simons levels K11 is Z2 level 2, as I described before. Whereas that for Chern-Simons, for the other two triplets of Chern-Simons levels, you can show that it is Z2 level 0. So what is our explanation of this phenomenon? Okay, so we expect that the different topological sectors arise from the different choices of polarization of the corresponding 6D n equal to 2,0 theory. Okay, so this is our explanation. Okay, so are there any questions about this section which I just ended? Okay, if not, I can proceed by taking into account two copies of T2 whose flavour symmetry is gauged with Chern-Simons levels satisfying the ATT condition. Now I will explain to you that actually these theories possess n equal to 5, SUSY, and indeed they are equivalent to a variant of the orthosymplectic ABJ theory. Moreover, I will also point out that by gauging particular discrete symmetries, we can also obtain theories with n equal to 6 supersymmetry. Okay, so let us start with the superpotential analysis, and let us see why n equal to 5 SUSY can be predicted from the superpotential. So let us consider these theories which I drew here. So which are Simons levels satisfying the ATT condition. So in 3D n equal to 2 language, where SO2R is manifest, the superpotential is the following. So basically it's similar to the superpotential, the case with only one copy of T2, but now you must take into account that we have two different moment maps corresponding to the two copies of T2. So I denoted them as mu with a capital I index, where the capital I index can be equal to 1 and 2 depending on the two copies. Now these moment map operators satisfy the same relation which they satisfied before, but so each copy satisfies independently such relation, and I wrote down the relation here. So we can use this to prove the enhancement basically. So proceeding as we did before, we can integrate out the adjoint scalars, and this is the effective superpotential. Now you see that the first term of the effective superpotential contains here in round brackets 1 over K1 plus 1 over K2 plus 1 over K3. Now, if the ATT condition is satisfied, this quantity is 0. So if the ATT condition is satisfied, we are left with the following effective superpotential. So you see that this case is a little bit different from before because the effective superpotential, when the ATT condition is satisfied, is no more 0. So there is a U1A flavour symmetry that assigns charge 1 to every chiral field of the first T2 theory and charge -1 to every chiral field of the second T2 theory. Or explicitly, the two moment maps carry charges 2 and -2 respectively. So naively, from the same argument as before, one might expect n equal to 4 SUSY enhancement. But actually it turns out to be n equal to 5. Indeed, it turns out that there is an SU2A, SO3A flavour symmetry that transforms the two moment maps as a doublet. So our symmetry is SO2 plus 3R, which is equal to SO5R, and SUSY is enhanced to n equal to 5. So actually we can show this also by using the index. And so let us define the index for Chern-Simons theories with two copies of T2. Basically, it is very similar in its structure to the one which I wrote down for a single copy of T2. But now we must take into account that we have the contribution of the two copies, and you can see that we have a fugacity A corresponding to the first copy, and a fugacity A to the -1 corresponding to the second copy of T2. And A is the SO3A fugacity. And we set A to 1 if the ATT condition is not satisfied, of course. Now, if the ATT condition is satisfied, we can study the contribution from the zero flux sector, and up to order x squared is the following. So the difference here, notice, is that the coefficient at order x is 1, is no more 0, meaning that the n equal to 3 flavour current is U1. And I point out that this is a necessary condition to have n equal to 5 SUSY enhancement. Okay. Now, in order to prove that actually we have SUSY enhancement, we have to look at the term at order x squared with a negative sign. This is the following. So there are 3 terms contributing with a negative signs. One of them, which are denoted in red, corresponds to 1 n equal to 3 flavour current. But then we have 2 extra terms, which are denoted in blue, and they correspond to 2 n equal to 3 extra SUSY currents, meaning that we have enhanced n equals to 5 SUSY. Now, if the ATT condition is satisfied, so for these general values of the Chern-Simons levels, we can study the Higgs and Coulomb branch limits of the index, as I did before, and we find that, first of all, that the Higgs and Coulomb branch are equal, as expected, for n equal to 5 SUSY, and they both describe a D-type Cranian singularity. Okay. Now let us consider the special case where the Chern-Simons levels are taken to be -k, 2k, and 2k. So 2 copies of T2, whose SU2 cube symmetry is gauged with Chern-Simons levels -k, 2k, 2k. Now this theory is equivalent to the, yes?
So if you go to the case of an n equals 5 enhancement.
Here or the previous slide?
Here,
Maybe.
I was just wondering,
Mm-hmm.
I don't see that there would be 2 different moduli spaces because the symmetry is no longer a product.
Yeah, okay. So the point is that what I do here, basically, I take the Higgs and Coulomb branch limits of the index as they are defined by Razamat and Willett. So I use their prescription. Basically, by studying such limits, you obtain basically 2 terms which are equal. This is what I mean by what I wrote down here.
But you won't be able to distinguish between a Higgs branch and a Coulomb branch, will you?
No, yeah, you are right. I call them Higgs branch and Coulomb branch simply because in the paper by Razam, yeah, it's simply because of that. You are right. They are not really Higgs branch and Coulomb branch. Yes, indeed.
And will you find a single moduli space, or you will find 2 different moduli?
I find the 2 of them separately. Yeah, I take both limits and I find them the 2 of them separately. This is how I did the computation.
The overall moduli space should be C4 mod E.
Exactly, yes.
And then you're basically taking 2 slices of restricting 2 variables.
Yeah, this is what
C4 modded out by D.
By the same,
yeah, by
I'm
D.
guessing. This
But
is
C4 basically yeah. So here I wrote that both of them are C2 mod dk plus 2, meaning that the full moduli space will be C4 mod dk plus 2. Yes.
So it's just like with 16 supercharges where you just like fake it in 3D and write a Coulomb and Higgs branch, but overall the remainder is the full moduli space.
So, would you expect to find a union, or you find a 4-dimensional space with a single singularity at the bottom? Klein, right? I mean, you're saying it's a product of 2 Kleins?
So no, I don't think so. Basically, the only thing which you are right that the terms Higgs and Coulomb branch, as I wrote them down here, are quite misleading. I think that, okay, the correct way should be to say that the full modular space is C4 mod dk plus 2. Yeah, probably there might be these two branches, because actually by taking the limits of the index, by using the prescription which I described, I obtain them. Then you are right that they are not actually Higgs and Coulomb branch.
Yeah, I see.
It's only an artificial way of calling them. Yeah.
And also, so it will be important to clarify whether it's a singularity where the action of D divides into two different spaces, or whether it's a combined action on all four coordinates.
Well, the thing that we studied, and so I can tell you this, is that one can study basically, so we know what the generators are. Basically, they are the generators of both what we call Higgs branch and Coulomb branch are. Basically, they are the same as before, the one I wrote down before. But since we have two copies of T2, they correspond to the ones are the generators with the chiral fields and the moment maps of the first copy. And the second one, which we find corresponding to the other branch, let's say, they correspond to the chiral fields and moment maps of the second copy. This is what we were able to study. Then, yes, for instance,
so it sounds to me that if you project four-dimensional moduli space on two different projections, you'll find the D-type singularity. Then it remains to clarify whether the full space, the full four-dimensional space, is some combined action, or is it?
Yeah, you are right. Yeah,
it should be completely the same as for 16 supercharges. But just there you have some C to the 4R mod some real reflection groups on Weil group, and then if you lower supersymmetry, there are some other reflection groups. And for n equals 5, it will be quaternionic, as there was this paper recently by Gabi
for
and
instance,
someone else. So then they would say here that this is C4 mod dk plus 2. And then you can, instead of taking 4 variables, you can just set 2 of them to 0, and then you find Higgs and Coulomb. These are just names you're artificially giving now. But from the index, it's natural to find these two limits. I think that's it.
I think the Shu understands it.
But maybe we can discuss this afterwards.
Okay. Yeah. I also have some more explicit maybe equations in the backup slides, maybe to discuss about this. Okay. So
thank you.
Okay, thank you. So let's go on. Okay, so let us consider two copies of T2, and we gauge the flavour symmetries with Chern-Simons levels minus k, 2k, and 2k. So now this theory is equivalent to the spin 4 level 2k times USP2 level minus k gauge theory with 2 bifundamental hypermatrix. And this theory is closely related to the IBJ theory, whose gauge group is O4 level 2k times USP2 level minus k. Now, it is important to point out that both the spin version and the orthogonal version of these theories can be obtained from the special orthogonal variant of the IBJ theory. In particular, the spin variant can be reached by gauging the Z2-04 magnetic symmetry of the special orthogonal variant, whereas the orthogonal variant can be obtained by gauging the Z2-04 charge conjugation symmetry of the special orthogonal variant. And the important point is that gauging appropriate discrete symmetries, SUSY can also get enhanced up to n equal to 6. So let us see this explicitly. Let us take this quiver, so this variant of the IBJ theory, for k equal to 1. Now, in the orthogonal case, we find n equal to 6 SUSY. In the special orthogonal case, we find n equal to 6 SUSY also, but in the spin case, we only find n equal to 5 SUSY. So, what is the lesson here? The lesson is that the global form of the gauge group is not a negligible part of the story. Indeed, the infrared CFTs corresponding to distinct global forms may possess different amount of SUSY. And I also reported the indices for these theories. Now, what you can notice from the indices is that, so let us consider for simplicity the unrefined indices. So this chi2 SU2 basically is a triplet of SU2, meaning that in the spatial orthogonal and orthogonal cases, the coefficient at order x is equal to 4. Okay. Now, the fact that the coefficient at order x is equal to 4 is a necessary condition for n equal to 6 SUSY enhancement. And indeed, by studying the index in more depth, for the SO4 level 2 times USP2 level minus 1, and for the O4 level 2 times USP2 level minus 1 gauge theories, we find that they actually possess n equal to 6 SUSY. On the other hand, if you look at the index for the spin 4 case, you see that the coefficient at order x is equal to 1. And if you remember, this is the necessary condition to have n equal to 5 SUSY. So the lesson of this slide is that gauging discrete symmetries and considering different global forms is something which should be done and is not just a negligible part of this story. However, if we take K, the Chern-Simons level, to be bigger or equal than 2, we always find that all of these global variants always possess n equal to 5 SUSY. Okay, so finally, let us consider also the one-form symmetries of our Chern-Simons theories with 2T2 and levels minus K to K to K. Now, actually, the one-form symmetries and their Hooft anomalies can be derived exactly as before, so as in the case with one copy of T2. So one finds that for K even, the theories has a non-anomalous Z2 times Z2 one-form symmetry, whereas for K odd, the non-anomalous one-form symmetry is Z2. And we can gauge the non-anomalous Z2 one-form symmetry corresponding to the centers of SU2 level to K and SU2 level to K. And now the resulting theory is equivalent to the SO4 level to K times USP2 level minus K version of the EPJ theory. And so basically we have the following diagram, which I drew here, and is the same as before. And this last step, so the bottom, which I denoted in blue, can be reached by gauging a further Z2 one-form symmetry, and this can be done only for K even. And actually, this last step in blue, why I highlighted it in blue, because if we take the theories with these gauge groups in blue, and we gauge either Z2 zero-form charge conjugation or Z2 zero-form magnetic, then we obtain theories which possess non-invertible symmetry. Okay. So, are there any questions about this last section which I described? Okay. So if not, let me just briefly mention about general TN theories gauged with Simons levels K1, K2, and K3. So I sketched them here. So the 3D TN theory, as you know, admits a Lagrangian description via the mirror theory, which is described by the following Quiver diagram. And for n equal to 3, this is the affine 6 thinking diagram with the 6 flavor symmetry in the infrared. Now we can compute the index of Chern-Simons theories with 1 and 2 T3 building blocks using the mirror description. And if the ATT condition is satisfied, the results for the zero flux sector of the index confirm the enhancement to n equal to 4 SUSY in the infrared. And here I reported the results for a single copy of T3 and 2 copies of T3 gauged with Chern-Simons level satisfying the ATT condition. Now, actually, this is quite an hard computation, and so we would have liked to do more on this. And maybe after the talk, if someone is interested in what can be done with the T3, for instance, we can discuss. However, so if you look just at the zero flux sector of the indices, you see that there is n equal to 4 SUSY in the infrared, if the ATT condition is satisfied, of course. So finally, let us do the conclusions. So we computed the index of Chern-Simons theories with T2 and periphery also with T3 building blocks. And this confirms the enhancement of SUSY when the ATT condition is satisfied. We studied the moduli space of such theories when the ATT condition is satisfied. And for a single copy of T2, the Coulomb branch is trivial, better what we call the Coulomb branch is trivial, whereas the Higgs branch limit of the index produces the Hilbert series of a D-type Cranian singularity. And for two copies of T2, both the Higgs branch and the Coulomb branch limits of the index yield a singularity of this type. Then we also showed that even if the ATT condition is not satisfied, there is an infinite family of theories that flows to the rank 0, 3D n equal to 4 T of X theories, along with a decoupled QFT. And interestingly, the known Lagrangian description of the T of X theories only has manifest n equal to 2 supersymmetry. We also analyzed one from symmetries and their Hooft anomalies, extracting information about the topological sector in the infrared. And, well, you might also recall that we also encountered bad theories whose index diverges, and studying them in more detail might lead to some interesting features. And finally, as I mentioned, compute the superconformal index for Chern-Simons theories with Tn building block with n bigger or equal than 3 is technically difficult. So it would be nice to develop some tools to study in depth this class of theories in the future. Okay, thank you for the attention.
All right, let's thank William. Do we have questions? Okay, so I can ask one. So you have you find the enhancement to n equals 4 and n equals 5 supersymmetry.
Yes.
Do you expect to find bigger enhancements for some very particular values, or do you have a way to rule that out?
For the T2 case, which is the one which I analyzed, I actually don't expect to find a big enhancement. The open point is the following one. So you recall that in the T2 case, I found a class of theories which possess which exhibit n equal to 4 enhancement, even if the ATT condition is not satisfied. One might ask, is this a general fact, which also holds for general Tn theories with n bigger than 2? Or is it just a special case which is only valid for the T2 case? Because you know the T2 case is in some case special since it is Lagrangian, whereas for n bigger than 2, the Tn theory is no more Lagrangian. And so I mentioned only briefly about the T3 case. We tried to compute the index of the T3 case for the same values of the Chern-Simons levels, which do not satisfy the ATT condition, but exhibit n equal to 4 enhancements in the T2 case. So Chern-Simons levels K1 and 1. And in the T3 case, we did not find any signal of SUSY enhancement from the index. Now, there might be two answers to this point. The first one is that, as I already said, this might be special only for the T2 case because T2 is Lagrangian. But the other answer might be that computing the index for the T3 case is hard. Basically, what we did is starting from this mirror description. So taking 3 copies of TSU3 and gluing them together. But actually in doing so, if we want to study the contribution of the index up to a certain order, we have to expand each copy of T3 before gauging it up to an even higher order and sum over a lot of gauge fluxes. So the computation is really difficult and takes a lot of time. So we are not sure about our computation for the T3 case when the Chern-Simons levels do not satisfy the ATP condition. So we didn't find any signal of SUSY enhancement, but maybe this is due to the fact that we should have summed over more magnetic fluxes for each of the three TSU3 building blocks of the mirror description. But this takes a lot of time, so computationally is difficult to do it. This is the open point, I would say, because for the T2 case, I don't think that there should be further enhancement. The only open point in the T2 case is regards the indices which diverge because they correspond to bad theories. I don't see why they should enhance to higher supersymmetry, but this is the only question. Yeah. I would say so that the open questions are related to T3 and generally to Tn with n bigger than 2.
And do you see any way to use some principal geometric engineering to address such questions, or is this too difficult?
Okay, so I actually I don't know them, but maybe they might be more useful than the index, because clearly the index is not the best way to study general Tn theories with n bigger than 2, as I said. So yeah, if there is some geometric engineering method, would be probably better and might give a certain answer, maybe. Yeah, but I am not aware of them, unfortunately.
Okay. Do we have more questions? Okay, then I would say let's thank William again.
Thank you very much.
And we can go off the record.